Hey, we're going to be going over some of the quantitative problems with Newton's second law, so how to use the numbers and everything, and a bit of a different background now. So here we go. So we are taking a look at all of the Newton's second law stuff, and so we're just going to hop right into doing some problems. Just a really basic one to start, and you're going to see that the actual process for how we do this stuff really isn't any different. The only difference is we're going to add some numbers at the very end. So this is just a ball that's hanging from a string. It's connected to like the ceiling or something like that, and then we want to draw for a free body diagram for the ball that's hanging. So first thing I do is I take a look and say, okay, what are all of the contact forces for this ball, right? So if I'm looking at that ball, then what I have is this force of tension that's going up on the ball in the direction of the rope, and that's the only thing that I have touching it. So when I go to draw this free body diagram, I have the force of tension that's going straight up, and then my long range force is going to be the force of gravity, which is going straight down. And the other additional thing that I can draw on this is I know that these two forces need to be equal in magnitude because those are the only two that I have, and this ball is just sitting there completely motionless. So that tells me that there's a constant velocity. So we can write constant velocity, and that constant velocity is 0. Like, it's not going anywhere, right? So what I can do is I can put little tick marks on those forces just to show that I know that they're equal to each other. So that's really all we could do if we were doing this qualitatively. The next thing I could do is I could set up my Newton's second law equations. So I know that in the y direction here, because those two forces are equal in magnitude, and there is no acceleration, Newton's first law tells me that the net force is equal to 0. Okay? And then in the x direction as well, there are no forces here in the x direction, so the net force is also equal to 0. But what we can do now is we can go and actually figure out some numerical stuff for this. So if the problem says, hey, this ball, let's say this ball has 5 kilograms of mass. So that would need to be something that's given to us in the problem. But if I know it's 5 kilograms of mass, the one thing that I can figure out, if I know an object's mass, right away I can figure out what is its force of gravity right there. From our equation, let's go do this in white. Come on. And if I just write it in white over here, let's see, get this going. There we go. Remember, my equation for the force of gravity, I'll write it up here, is the force of gravity is equal to something's mass times the pull of gravity. And this is what we call the gravitational pull, right? That is 9.8 meters per second squared. That's the acceleration of gravity for whatever planet we're on. So we're on Earth, so it's 9.8. And so if I want to figure out the force of gravity on something, I take its mass, which in this case is 5 kilograms, and then I take its acceleration of gravity, which in this case is 9.8 meters per second squared. And remember, we don't need to put the negative on it because we're only figuring out how big this force is. We already have it shown that it's going down, right, which would take care of a negative if we were going to put on it. And 5 times 9.8 is 49. So I know that the force of gravity has a magnitude of 49 newtons. Okay, so when I set this up in the y direction over here, so let's go in the y direction, right? The net force in the y direction is equal to 0. Well, now I can actually put in the forces, right? Going up, I have the force of tension plus the negative force of gravity because it's going down, and that's equal to 0. So what do I know? I know the force of gravity is 49, so I can substitute that in and say minus 49 newtons is equal to 0. So right away now I can solve for this tension force, and I can find out that the tension force is also equal to 49 newtons. So if just following that process of using Newton's second law, I'm able to figure out, all right, the force of gravity is 49 newtons and the tension force going up is also 49 newtons, and that's why they're both canceling each other out. Okay? If we wanted to make this not just a y direction problem, maybe a little something more. Okay, we have this guy, he's pushing on a fridge, and he's pushing it at a constant velocity of 5 meters per second. So that right there is important to me, because that tells me, if I can get this to switch colors. I don't know why it's not wanting to switch colors today. Nope. All right. Red, give me the red one. There it is. Okay, that tells me that the net force is equal to 0, right? Constant velocity, Newton's first law. If something's motion is not changing, then I know the net force is 0. So I want to look at this fridge because I'm going to try to figure out all the different forces that are acting on it. So I'm going to be looking at that fridge and thinking about what are all the contact forces on this fridge, right? Well, we have the guy pushing it with some push force, right? We have the ground, which is pushing up on it with a normal force, and that's making sure the fridge doesn't fall through the ground. And then this is sliding on the ground right here. All right, we know that it's in contact with the ground and it's sliding, so there's going to be some type of friction force as well. And that's moving, so it's kinetic friction. And so when I go to draw my free body diagram for that fridge, I have a normal force that's going perpendicular to the ground. I have a force of push, and that's totally horizontal. And it also told us that he's pushing with a force of 125. So we know this is also 125. We know there's a friction force. And my long-range force is force of gravity from the Earth pulling down on the fridge. Okay? And so, again, here when we talked about that it's a constant velocity, that tells me that the overall net force in that direction is equal to 0. Okay, so this is where we set up our two equations. We know in the x direction, let's go white. In the x direction, our net force is equal to 0 because there's no acceleration. Right? We also know in the y direction, our net force is also equal to 0 because, again, there's no acceleration. So it's not flying away up, it's not accelerating down or anything like that. So both directions have a net force equal to 0. And that's going to help us set up and figure out the numerical value for each of these forces. So if I know that the push was 125, right, now I just set up those different equations. I say, okay, the force of push plus the friction force, and it's going in the opposite direction, so it's going to be negative. Those need to be equal to 0. Okay. In the y direction, we have a similar type of thing. We have, well, the normal force is going up, so it's going to be positive, and we're adding everything plus the negative force of gravity, and that also needs to be equal to 0. They're canceling each other out. So this is like the simple version where we only have 2 in each direction, which makes things nice. Okay, and so now I just plug in my numbers. Right? I know that the push force we said was 125. So 125 newtons minus that friction force, and that's only in the x direction, is equal to 0. So when I solve this, I do a little abracadabra, right? I solve for that missing friction force. I'm going to find out that the friction force is also equal to 125 newtons. Okay, so there's one of my missing forces that I don't have. Over here in the y direction now, what I'm looking at is seeing, okay, do I know anything to figure out force of gravity? It's usually like where one of our first steps is. And we know that this is 50 kilograms, right? We know the mass of the fridge. So we can use our equation for the force of gravity. Right? Force of gravity is equal to something's mass times the acceleration of gravity. On Earth, it's 9.8. So this is going to be 50 kilograms times 9.8 meters per second squared, which would be 490 newtons, right? We just plug that into a calculator real quick. So we would have normal force over here minus 490 newtons is equal to 0. So we just do that one little step, we can solve, and we're going to find that the normal force is equal to 490 newtons as well. Okay, so when things are going at constant velocity and everything's all balanced out, it ends up becoming not too bad of a problem. Okay, this same process, no matter what we're doing, all you need to do is draw that free body diagram, put whatever numerical values that we know or that we can figure out onto it, and then set up your equations and be able to solve for any missing pieces. All right. In the next video, we're going to be going over what if one of these things is at an angle. So I will see you there.